Vectors. Question 1 from the Vectors Step 2 support module is this question here. And so let's just go straight into it. We've got lines M1 and M2 passing through the origin. So if we write those as lines, that's going to be 0, 0, 0 to start with, plus however much it takes to get to I plus j, which of course is 1, 1, 0. So M1 is this. I'm just using the letter A to denote that constant there. And M2 is, of course, I don't need to write the 0, 0, do I? But M2 is just going to be, therefore, B into 1, 0, 1, something like that. Find the directions of the two lines M3 and M4 that pass through the origin as well, and make angles pi over 4 with both M1 and M2. So we're going to have to use the A dot B equals mod A mod B cos theta idea here. And if we just say M3 has direction, or it has, the line is C, X, Y, Z, because it goes through the origin again, so it's still just 0, 0, 0 plus this. X, Y, Z, just denoting its direction. I know those aren't great letters to choose, but I'm going to use them anyway. They were easy for me to type. So now we know that like this direction dotted with this one, with the sizes of each directions times cos of pi over 4 is a thing that works. So okay, that means x plus y equals this. Root 2 cancels with the root 2 that comes from this, because this is 1 over root 2. And you just end up with this. And the same thing for the other one when you do this with this one here. You get the same sort of thing and you end up with this. The first thing you can notice pretty much immediately is that, of course, this is the same as this. So x plus z equals x plus y, which means, of course, that z must be equal to y. So that's quite helpful. So we can put that into there. If you put, so I put z into here just to make it, I put z equal to y into here. If you do it over here, you get the same thing again. So now we have one equation with two unknowns, which means we don't really have much choice but to just choose a value for one of them. So let's just choose x to be 1 and then solve for y. Square both sides and do some rearranging. Factorize to get y into y minus 2, so solutions are y equals 0, y equals 2, which means our z solutions are also 0 and 2, which means the two directions are 1, 0, 0, and 1, 2, 2 for our first part. And then it says find the cosine of the acute angle between them. So again, we're just going to use this, dot them together with their mods. Root 9 comes from the 1 squared plus 2 squared plus 2 squared, of course. This makes 1, because the zeros help out. That's 3, so it's 1/3 is cos theta. And we'll be good to go. The points A and B lie on M1 and M2 respectively, and are lambda root 2 away from O. So okay, they're on M1 and M2, which are just these equations here. This is the entire equation of the line. So how do we get lambda root 2 away? Well, let's just do a distance formula for this. Let's just say, I mean, this can be written as a squared, sorry, this can be written as a0, can't it? So that means a squared plus 0 squared is equal to lambda root 2 all squared, right? So wherever you are on this thing here, I'm finding the a value for which we're this far away, I guess, is what I'm doing. So okay, well, that just turns into this, and then it says that everything's non-negative, so we're just going to say a equals lambda, I guess, and therefore say that the point in which we are at a is lambda, lambda 0, because I worked out a is lambda, so I just put that in there, and I'll get that we're at lambda, lambda 0. I can do the same for b, which is about m2, so it's going to be b squared plus 0 plus b squared equals lambda root 2. It's the same thing. Everything works out the same, pretty much. And then the other ones are actually easier, partly because they're only distance 1 away, but also because, you know, this is quite an easy one to use. Sorry, no, this one is quite an easy one to use, isn't it? You have c squared plus 0 squared plus 0 squared equals 1 squared. So c is just going to be 1, obviously. Everything's positive, remember. And this one here, a little bit more complicated. We're going to have d squared plus 2d squared plus 2d squared, all squared, of course, those things, equals 1 squared, because again, it's 1 away. You have, I think, what, 4 plus 4, 9 d's here. So when you divide by 9 and then square roots, you're going to get d is 1/3. So therefore, this is at 1/3, 2/3, 2/3 is our point Q. So those are all of our points. And now we're being asked to show that there are two values of lambda for which AQ is perpendicular to BP. So AQ is, of course, the vector Q minus A, which is this. It doesn't actually matter which direction I put that in, but it's okay. And BP is P minus B, which is this, a bit easier. And of course, for two things to be perpendicular, that means in vectors, A dot B is 0 for perpendicular vectors. So this means we want this vector dotted with this one to be 0. So it's going to be this times this, plus this times this, which is 0, which is very nice, plus this times this. And if we just expand that out and collect together some terms, minus 4/3, minus 2/3 is minus 6/3, which is 2. And then I just completed the square here. I mean, maybe I didn't even need to go as far as this. I just completed the square very quickly and then moved some stuff over and worked out this. So yeah, that's two values of lambda. maybe I could have stopped here, but I guess I need to show, maybe I could have just checked the discriminant, I guess, to show that it was positive, and that would be good, because they didn't actually ask me what the values of lambda were, did they? So anyway, we get lambda as this, and we're all good to go. Next, we need to prove that there are no non-zero values for lambda for which AP and BP intersect. So the line AQ is, let's start here, and then let's add on some direction of this minus this. So that's what I've done. So that's the line AQ, starting at this point, adding some amount of this minus this. BP, same thing, except for BP, I'm going to start here, because that just might make my equations a little bit easier. If I started here, because like the direction is basically the same, it's just this minus this, right? But if I start here, I get a couple more lambdas in here, and I think this one's a nice one to use. So I'm going to start there instead, and I think that's a wise thing to do. Anyway, now of course we need the x coordinates, the y coordinates, and the z coordinates to all be equal at the same time. So we're going to have these three equations. This is just the top line equal to the top line, middle line equals middle line, bottom line equals bottom line. And now you just need to find the least painful way you can of solving this triple simultaneous equation. I must admit, I did not find a very non-painful way of doing it. I mean, first, I simplified up these a little bit. So I times them all by 3, essentially, is I think all that I did there. Yeah, I just times them by 3. And then I said, well, okay, why don't we just rearrange this for A and just shove that result into these two? Because I genuinely, I thought for a while about doing this one minus this one, and I wrote some stuff down just because almost everything cancels except for the A. It just didn't really help. So I just then decided to do this, just shove the A's in. And then we can simplify these up a bit. So just expand out and collect together, and then expand out and collect together. And now we have these two simultaneous equations that are just in B and lambda. So, okay, that's better. It's a two-dimensional simultaneous equation, at least. We can notice that things sort of match here. At least those two and those two do, which is fantastic. So let's just take them away. 3/2 minus 3 is 9/2. And this minus 0 is this. And now I can rearrange this for B, of course, just by moving the B over from here and then factorizing and dividing, and we end up with this. And now I'm just going to shove that B into the better of the two equations here, which I think is this one. Just going to shove that value for B in there. Times everything by 9 lambda minus 6, of course. Seems like a sensible thing to do here. We end up with this. Looks good. And then, of course, we can expand out and rearrange and collect, and then factorize out the lambda and get answers of lambda equals 0, or lambda equals 36/54, which is 2/3. Now, why does it say there are no non-zero values for lambda that work? Well, here's the 0 one, so that's fine, but that's non-zero, so why have I got that? Well, the answer's staring you right in the face. It's because of this thing that we had earlier. This b is 9 lambda minus 6 on the denominator. If lambda is 2/3, then this makes 6 divided by 0, and the b value is not defined. So this actually isn't a solution, and therefore there are actually no solutions to this, no non-zero solutions to this, I should say, that would make this work. Thanks for watching, and I'll see you next time.